So turn off your camera too, if you don't mind. Thanks. All right, so talking about optimization with Ritvic here, and let's just get after it. Find all the extrema of f of x on the interval from -1 to 6. So to find the extrema, we need to find the derivative, right? And then we have to set that derivative equal to 0, correct?
Yeah.
Okay, so Ritvic, tell me how do I find the derivative for this particular one? You walk me through it.
All right, so you have to use the quotient rule. So starting with the numerator, you take the derivative of the numerator, which is so you distribute first. So it'll be x squared minus 5x over x plus 4. And then
Good.
from there, you take the derivative of the numerator. So 2x minus 5.
Mm-hmm.
And then you multiply with the denominator x plus 4.
Mm-hmm.
And then subtract the derivative of the denominator, so x, and then multiply with
just 1, not x.
Oh yeah, sorry, my bad. 1.
Mm-hmm. Mm-hmm. So
And
1
then,
times x squared minus 5x. Good. All
yeah,
over what?
and then divide over x plus 4 squared.
Perfect. So let's simplify that just so that it's a little bit easier to work with. So that's x squared. I'm distributing or foiling. 2x squared plus 8x minus 5x minus 20.
Yeah.
And this is minus x squared and plus 5x. So in total, it's going to be x squared. This is 3x plus 5x is 8x minus 20, right?
Yeah.
All over x plus 4 squared. Okay.
Yeah.
And that's pretty nice because now the numerator is going to factor, isn't it?
Yeah.
That's going to factor into x, what, plus 10 and minus 2?
Yeah.
Okay, good. So that's a really nice way to look at it, because now, how do I know where the derivative is equal to 0? What do I do to find that?
So you have to factor the numerator and the denominator.
Mm-hmm.
So it will be, and set them to equal 0. So it'll be x equals 10 and -10 and 2.
Good. So I should say where the derivative is 0 or undefined. Yes.
Yeah.
Okay. So that's what you're saying. Good. So x plus 10 equals 0, x minus 2 equals 0, and x plus 4 equals 0. So x equals -10, x equals 2, and x equals -4. Those are all my critical points. Or those are all my, potential critical points, right?
Yeah.
Okay, and now let's look at what it said over here in the directions. It said on the interval from -1 to 6. So we can actually get rid of this and this because that's not in the interval, right?
Yeah.
Not in -1 to 6. So that's why I'm getting rid of both of those. So really, I just have to look at 2, and that's it. So 2 is my extrema, but they probably want the actual point itself. They don't want you just to write x equals 2. So now let's go plug that back in. So let's find f of 2. Is this what your teachers want you to do?
Yeah. So for that, I got -1.
2 times -3 all over 6, which is -1. Good. So your point is 2 comma -1. So there's your extrema. Now they might want you to say whether it's a max or a min.
Yeah.
Do you know how to do that?
So you have to draw a number line with the leftmost point being -1 and the rightmost point being 6, and then 2 in the middle.
And so we're going to find out what we're going to just take some point. Let's take 0, for example, and let's take 3.
Yeah.
So you're going to take the derivative at 0. So plug in 0 into your derivative function, which is up here to the right. If I plug in 0 to that, I'm going to get, we can actually plug it into this one. It'll be easier to plug it into this one. It's just going to be negative 20 over 4 squared, which is 16. So it's going to be negative 20 over 16. And the main point is we just want to know what the sign is. Is it positive or negative?
Yes.
And
negative.
that's negative. So that means it's decreasing, right?
Yeah.
That's what that negative means. And so then we look at f inverse of 3, or the derivative at 3. And we look at what's happening there. And when I plug 3 in there, you can really just plug it into here. You can plug it into this one as well and just use sign analysis. So this is going to be a positive, that's going to be a positive, and that's going to be a positive. So a positive over a positive is positive. Have you learned that trick?
Yeah.
Yeah, so you could actually, it probably is fine just to leave it in the factored form and just use that trick, but I like just plugging 0 in right here. It's much easier. So since it's down and up, what kind of point is that? Max or a min?
That would be a max. Oh, sorry, min.
Yeah, it's going to be a minimum. Going to be a minimum, should say minimum point. Is that all we needed to do?
Yeah, I think so.
Okay.
So finding all the extremas.
What did you have a hard time with? What do you struggle with there? Seems like you were getting that right.
So yeah, I got 2 points off for that question because my teacher asked, what about x equals -1 and 6?
Oh, got it. Yes, because they're asking on the interval. That's why.
Oh.
So because it's a closed interval, you see how it's a closed interval?
Yeah.
That means that you would want to see how you have the closed interval there.
Oh, because of the brackets, they're included.
Because of the brackets, those are included. So you're going to have a maximum probably on each one of those. Definitely, you're going to have a max on each of those.
Oh, okay.
Because the min was here, it's got to do something like, it's somehow, because there's no other maxes or mins on this interval. And it's going down here and up here. So that point was -2, 1, or 2, -1. So your point, and I'm going to just draw it in here, make this 2-dimensional. Your point was there and it was going down from here and up from there. So those are going to be maxes at -1 and -2. So you should find what f of -1 is. So let's just plug that in. That's going to be 1 plus 5 all over 3, which is 2. So the point 1, 2, sorry, -1, 2 is going to be a max point. And then plug your other endpoint in there. Yeah, I forgot about endpoints when it's a closed interval. So plug 6 in, you get 36 minus 30, which is 6 all over 10. So 6/10, which is 3/5. So 6, 3/5. So those are your max points.
Oh, okay.
So your max points are going to be at -1, 2 and at 6, 3/5. These are maximums. On that, just on that interval, those are maxes. And the reason you know that is because you saw that there were no other extrema. There are no other extrema in this interval, so it can't level out and go back up again or something. Because if it did, you would have found that point when you did this analysis up at the front. That makes sense?
Yeah.
So your next, can we move on to the next one?
Yeah.
Uh-oh, didn't mean to do that. Just gonna move it a little bit so I can see it better. Okay, so it says analyze completely in graph. So, well, you can see that it's a, we're gonna wanna find the derivative. So the derivative, f inverse of x. Can I just do this quickly here? X squared minus 2x minus 3.
Yeah, wouldn't it be f prime of x, not inverse?
Sorry. Yeah, I don't know why I wrote inverse. Oops. Thank you. I've been working with inverses, and my pre-calc kids are doing inverses. So yeah, f prime of x, the derivative. Yeah, not the inverse. Which, thanks for pointing that out, so we didn't have that mistake running through the entire video. So write x and x. We're going to write -3 and +1. So you know that 3 and -1 are my maxes or mins.
Yeah.
And specifically, so we'll call this extrema. X equals and x equals. So, and then if we take the double derivative, well, let's go ahead and find out what's f of 3. If you plug that in, let's see, you're going to get, if I plug in 3 here, one of those 3's is going to cancel. So this is going to be 9 minus 9 minus 9 plus 5. So it's -4. And f of -1, if I plug that in, I'll just do the work over here. -1 is going to be -1/3 -1 plus 3 plus 5. So that's 8, that's 7, that's 6 2/3. 8 minus 1 is 7.
I got
8.
8 2/3.
So 8 minus 1 is 7, minus another 1/3 is 6 2/3.
Oh yeah, yeah.
Right. Did I do that right?
Yeah.
So those are my absolute. So let's figure out if those are mins or maxes. Well, we actually can do that without using a sign chart like we did in the or a real number line and sign analysis. We can do that just by looking at the extreme, at the fact that it's an odd degree and it's a positive leading coefficient. We know it's going to go up from left to right. So we know if these points, let me show you on a graph here. You know that the points, if I graph the original function, let's graph the original function in red. You know the original function has to go, well, you know some of the points are 3, -4. So there's one of your points, 3, -4. And another one of your points is -1, 6 2/3, right there. -1 and 6 2/3. Those are on my function, my f of x, right? See, let me put those in red so you can see that those are going to be f of x, right?
Yeah.
So, but I also know that it's going to go up from the end behavior. You remember how the end behavior tells you, if you look at the degree of your polynomial function and the sign of your leading coefficient,
Mhm.
you know it has to be going up to the right and down to the left. But these have to be maxes and mins, so you know it's going to be something like this. In fact, let's go ahead and just put in some other points we know. We know the y-intercept is right there. There's 5. Right.
Yeah.
We could find x-intercepts as well, but they're not actually ever asking us to do that. So let's not waste the time doing that. Instead, they're wanting to know inflection points and different things like that. So let's just kind of rough sketch the graph in here so we know what we're looking at. Let me try that again. There's what my graph is going to look like roughly. Okay.
Okay.
So what the absolute min is none because it's going down forever. Do you understand?
Wait, why is it going down forever?
Because look at what it's, look at where it's going. It's going down on the left and it's going up on the right.
Oh, so does absolute refer to the endpoints?
Absolute just means on the entire graph, what's the lowest point on the entire graph?
Oh, okay. So that
And
would
can
be,
you, and you can't say that, right?
yeah,
You can't say that the lowest point is something because it goes down forever.
gotcha.
If it was an even, if it was an even degreed function, then there would be a max, a min point or a max point potentially, because both ends would be going the same direction. That makes sense?
Yeah,
But when it's an odd degreed function, polynomial function, it's never going to have an absolute max or an absolute min, because the end behavior is to infinity in opposite directions. Okay.
yeah.
Now the relative maxes and mins we can find. The relative, as we just talked about, this one is -1 comma 6 2/3. So that's the relative max, -1 and 6 2/3, and the relative min is 3 comma -4. Now for the inflection point, we're going to have to take the double derivative. So I'm going to do this in green. So the double derivative is just taking the derivative of the derivative, and that's just going to be 2x minus 2. And if we solve this, 2 times x minus 1 equals 0, we get that x equals 1. So we know that the inflection point is going to be, now let's take f of that function. What's f of 1? Plug it in. You're going to get 1/3 minus 1 minus 3 plus 5. So that's going to be 2, what's that going to be?
4/3.
2 minus 1. Yeah. 2 minus 1 is 1 minus 1/3. No, it's 2/3, I think.
Oh, my bad.
Right? Because these are -4 together, plus 5 is +1. Oh, sorry. No, and that's not a negative. It's not a -1/3. No, you were right. It's 1 1/3 or 4/3. Yeah, you were right. So your point is going to be 1 comma 1 1/3. That's going to be your inflection point. 1 comma 1 1/3. Okay.
Yeah,
So you can see your inflection point right here. That's where it changes from concave down to concave up. That's what the inflection point is. Okay.
yeah,
So the increasing intervals would be from -infinity, because it's increasing when you jump on the graph, it's increasing there to there, and then from here to infinity. So the increasing is from -infinity to, and remember, you're doing this in terms of x. So what's the x coordinate? -1. Union. So use the union symbol from 3 to infinity, because remember, we're using the x coordinates. You understand that?
yeah.
And where is it decreasing then?
-1, 2, 3.
Perfect. And where is it concave up?
From 1 to infinite.
Good. From 1, that's right. I'm gonna put my point on here. There's 1 comma 1 1/3. That's my inflection point.
Mm-hmm.
So from 1, yep, from 1 to infinity, it's concave up. And where's it concave down?
-infinity to 1.
Perfect. You got it.
Yeah.
Okay. Clear on all that now?
So if
Oh,
you were
sorry.
to use a number line regarding point of inflection, how would that work?
So if you wanted to use a number line for the inflection point,
Yeah, to find the concavities.
okay. I mean, I see if you didn't have the picture itself.
Yeah, like if you
So
wanted to double
put
check.
your inflection point in here. and plug in, remember, you're going to have to point. So this is your inflection point. And plug in a number to the left of it and a number to the right of it. And plug it into the double derivative. The double derivative at 0, if I plug 0 back into the double derivative here, I would get a negative number. That means it's concave down. And if I plug in 2, I would get a positive number. That means it's concave up.
Okay, yeah.
That's how you would do that. Good question. All right, what is the largest possible area for a right triangle whose hypotenuse is 5 centimeters long, and what are the dimensions? All right, I'm gonna make this 2 different, if that's okay with you. I'm gonna duplicate this. Or did you already duplicate it?
You can duplicate.
Okay. I'm gonna duplicate it and I'm gonna make it a little bit bigger. I'm gonna delete that one and make this bigger. All right, what is the largest possible area for a right triangle whose hypotenuse is 5 centimeters long? Well, let's draw it first. So here's a right triangle. Now, I don't know what my x and y are, but I know the hypotenuse, whoops. I know the hypotenuse is 5. That doesn't change. That's not variable. I'm going to call these A and B, but I know that A and B do change. I'm trying to maximize the area. So let's first of all find an area equation in terms of A and B. What's the area equal? What's the area of a right triangle?
XY?
It's 1/2. I'm calling them A and B. It's 1/2, or if you want, I can call them X and Y. You want me to call them X and Y? I'll do that. We'll call this X and I'll call that Y. So it's 1/2 XY, right?
Yeah.
But this is not helpful because I want this to be written in terms of only one of the equations or one of the variables. So how am I gonna write this in terms of only one X or Y? How can I do that? Any thoughts?
I have no clue.
So here's the trick. You have to actually come up with another equation that relates X and Y together. Can you think of an equation that relates X and Y together?
The Pythagorean Theorem.
Perfect. So X squared plus Y squared equals 25, right?
Yeah.
And now let's solve this one for one of them. Doesn't matter, X or Y, doesn't matter. We'll solve it for Y. X squared equals 25 minus, sorry, Y squared equals 25 minus X squared, which means Y equals the square root of, and it's going to be the positive square root of, because Y is a positive number. It's a distance, right? 25 minus X squared. So you don't actually have to put the plus or minus in there. Now, why did I do that? Because now I can rewrite my area in terms of just Y by plugging in in terms of just X, not X. I can rewrite my area in terms of just X by plugging in for Y that new formula we just came up with. That makes sense?
Yeah.
And now see, we can max it. So that's the area of this right triangle in terms of X. So if we want to find the largest possible area, we're going to take the derivative and then we're going to solve that for 0. And that's going to tell us the max or the mins. Okay, so let's do that. So the derivative of this, we're going to have to use the product rule, right? So it's the derivative of the first times the second plus the derivative of the second. So I'm going to have to do a little bit of chain rule in here, right?
Yeah.
Do you need me to show you the little work I'm doing here as I do this?
No, it's fine.
Okay, so 25 minus, I'll do it in red, to the 1/2 power. So if that's y, well, let's call it u, not y, because I've already used. If that's u, then u prime is going to equal 1/2 times 25 minus x squared times the derivative of the inside, which is what, negative 2x. So that just equals negative x times 25 minus x squared. Oops, sorry, I didn't do that right. To the negative 1/2, my bad. Jeez, that was a bad mistake. Remember, I have to subtract 1 from that. Does that make sense?
Yeah.
So my derivative is actually negative. So it's really negative x, the 2's and the 1/2 canceled, all over the square root of 25 minus x squared. That's the derivative. And then I'm going to multiply that by 1/2 x, which was my first function. So I can actually put the x, I can make this x squared, and I can make that a 2 down there to clean it up. You understand how I did that?
Yeah.
Okay, now this looks like a fun little piece of junk, because now we're going to have to find out how to set that equal to 0. So this is where what comes into play here is I'm going to duplicate this too, so we can see this, because I'm going to need some work here. This happens in calculus quite a bit. You're going to have to clean up. You're going to have to use more paper than you wanted to use. So starting what I had at the bottom, so that's where I'm starting. So I'm going to write that back at the top, but I'm going to simplify it. So I will multiply. I'm going to use a blue pen here. I'm going to multiply this by this one right here by, actually, you know what? This 2 is already underneath here, isn't it? There's the 1/2, you can just put the 2 at the bottom, and that's already there. So I'm just going to multiply this by the root 25 minus x squared on the bottom and the top, so that I get a common denominator. Follow? Follow what I did there? I'm just going to keep doing it. You stop me if I'm losing you, okay?
All right.
So when I multiply these two together, voila, the square root goes away. So it's really just 25 minus x squared on the top, minus, and this red one over here isn't, it's just minus x squared, minus x squared. And on the bottom now, I have the common denominator, which was 2 times the square root of 25 minus x squared. So that's actually what, and actually I'm not even done simplifying, because that really just means it's negative 2x squared plus 25 all over 2 times the square root of 25 minus x squared. That's my derivative. Got it? Unless I made a silly mistake somewhere, but I don't think I did.
Yeah, I got it.
So how do I maximize that? I find out where it equals 0, right? I want to set that equal to 0. So how do I set the derivative equal to 0 if it's a fraction like this? What makes that 0? Does the denominator matter?
I think you multiply by the denominator on both sides.
Nope, don't even need to do that. All I'm trying to do is find out where this thing equals 0. How do I find out where this thing equals 0? Does it even matter what is in the denominator?
Oh no, it doesn't.
It doesn't matter, because all that matters is making the numerator 0. In fact, I can't make the denominator 0, because that would be undefined. So I'm trying to find out where the numerator equals 0. So that's all I have to do. All I have to do is take the numerator and set it equal to 0 and solve. So solving would be subtracting 25 from both sides, dividing both sides by 2, and then taking the square root of both sides. Now, I don't have to consider the negative square root because again, so technically plus or minus the square root of 25 is the answer. So that's, what is that, 5 over root 2 plus or minus 5 over root 2, which is 5 root 2 over 2. And again, I can ignore the negative because I'm talking about an area. I'm talking about an area which is a positive number, not a negative number. So what is the largest possible area? The largest possible area, well, we haven't found the area yet. We've just found the x coordinate. Now I have to go and use this to find the y coordinate. And then I can use those to find the area. Make sense?
Yeah.
So I'm going to take this number. I'm going to go back and look at my equation and remember the area equation. I could write the area in terms of x, but really I'm just going to use x squared plus y squared equals 25. I'm just going to use that to solve for it. So let's solve for y now. I'm going to do it up here. Solve for y. So we know x squared plus y squared equals 25. So all I'm going to do is plug in what my new x is. 5 root 2 over 2. Actually, you know what? Let's just write it as 5 over root 2. 5 over root 2 squared plus y squared equals 25. So that means 25 over 2 plus y squared equals 25. So now we're going to subtract. Y squared equals 25 minus 25 halves. Well, that's just 25 halves again. So guess what y equals? It equals the same thing that x equaled, 5 over root 2, which shouldn't surprise you. Well, maybe it will, but it doesn't surprise me. So the y and the x are actually the same thing. It's actually a square. It's actually an isosceles right triangle that maximizes the area. And again, that shouldn't surprise you. That kind of makes sense, that it would be like a square right triangle or an isosceles right triangle. So what is the area then? So there's my y. So what is the area? Remember, area is 1/2 base times height, or x times y. So it's 1/2 5 over root 2, 5 over root 2, which equals 25 over root 2 times root 2 is 2 times 2 is 4. 25 over 4 centimeters squared. And don't forget to put centimeters. And there's your answer. Sorry, I jumped all over the place, but did you catch that? You follow that?
Yeah, I follow it.
Awesome. All right, next question. Now we're going to delete this one and work on the other one. All right, so this says a rectangle has its base on the x-axis and its upper 2 vertices on the parabola. What is the largest area the rectangle can have, and what are its dimensions? Sorry. So we've got a parabola here. Let me just draw it so you can, so you can envision what they're saying here. So this is a upside down parabola shifted up 12, right? So here's 12 right there, and it's an upside down. Let's see where it says base on the x-axis. Okay, so it's going to be like this. That's what I have. Okay. And square root of 12 and negative square root of 12 are these numbers here, just so you know. The square root of 12 and negative square root of 12, I believe, are those numbers, right? Where if I set those equal to 0. So it says, what is the largest? So a rectangle has its base on the x-axis. So this is my rectangle. And its upper 2 vertices are on the parabola. So my rectangle, it could be like this, You see what I'm saying?
Yeah.
Or it could be like this. It's basically a rectangle, so it's got to go straight up from here, but the base is on that. A rectangle. So it can't be here because that wouldn't be able to create a rectangle. It's got to be somewhere inside of here. It could be like right here, like that, right? But that's what we're looking at, okay? So it says, what is the largest area of the rectangle we can have and what are the dimensions? So the trick to this one is to figure out, like I did on the last one, what the equations are going to be. So let me just draw it and let's see what this means. So it says it's a rectangle. And if it's a rectangle, then this distance has to be the same, right? The top and bottom distance have to be the same. You follow what I'm saying? That distance and that distance have to be the same in order for it to be a rectangle. And because this is centered, the axis of symmetry is on the y-axis, you know that these distances right here have to be the same also. That distance has to be the same as this distance right here. It's got to be symmetric, in other words. Do I have to explain that more, or is that pretty clear?
No, I got it.
Okay, so it says, what is the area of the rectangle? So what we're going to try to do is we're going to have to write the area of this rectangle in terms of x and y. So the first thing, let's call this x right here. Let's call this x. We're not going to call the full thing x. We're just going to call the bottom part x, or just half of it x. Okay, I think that'll make it easier for us to do. But this is going to be our y right here. The full thing is going to be our y. So what's the area of this triangle? It's equal to 2 of the x's by how I've labeled it, right? It's equal to 2x times y. You understand how I came up with that?
Yeah.
Okay, that's pretty important because that's going to make it easier. And the reason I wanted to do that is because this point right here is x comma y. And this point over here is negative x comma y. And we want to know how those are related to each other. Well, they're related to each other by this equation right here. So how are x and y related to each other? Y equals 12 minus x squared. So when I rewrite this area equation in terms of just x, you understand what I'm saying? I'm going to substitute in, instead of writing x, I'm going to write, or instead of writing y, I'm going to write 12 minus x squared, because that's what the y coordinate is equal to. So my area, if I distribute this, is equal to negative 2x cubed plus 24x. And now what can I do with that equation? If I'm trying to maximize the area.
Do we use the perimeter equation?
Nope, don't need the perimeter. That's my area equation. I'm going to just take the derivative, right? Because that derivatives help us find max and min points. So taking the derivative of this, I get negative 6x squared plus 24. Setting this equation equal to 0 will maximize it. So let's take out a negative 6, and that would be an x squared minus 4. And what do you know? X plus 2 and x minus 2. So x equals negative 2 and positive 2. So what is this distance right here? What is this, the distance x right here?
2.
It's 2. Now, if x is 2, what's y? I plug it in, right?
Yeah.
Y is going to be 12 minus 4, which is
8.
8. So y equals 8. So the area is equal to 2 times 2 times 8, which is 4 times 8, which is
24.
4 times 8,
Oh,
which is
sorry, 32.
perfect. Yeah, that's all right. I almost did the same thing. So it's 32. They didn't give us units. So we'll just call it units squared. So the largest area of the rectangle that you can draw inside there would be that where your points were 2, 8 and -2, 8. That's the biggest area you can draw. Good with that?
Yeah.
All right, let's do more. I don't know how much time we'll have for this, but by the way, do you have the answer keys for these?
Yeah, I do.
Okay, were those both right?
Let me check.
If they weren't, just don't tell me. I don't even want to know. I'm kidding. Do tell me. Occasionally there are mistakes that I make, but I'm pretty sure I did those ones right. So do you see the
Yeah,
pattern?
you're right.
Yeah, do you see the pattern? Do you see how we're doing this? We're coming up with an equation that we're trying to maximize, and then we're finding ways to make that equation written in terms of just one variable. And then we're taking the derivative of that equation, and then we're solving it for 0. That's the plan behind all these optimization problems. Okay.
Oh,
And the
okay,
trick sometimes is to find what that equation is that relates the X and the Y. So for this one, the equation that related the X and Y was easy. They gave it to us. For this one, the equation that related the X and the Y, we had to come up with, we had to realize, oh, it's a right triangle. So Pythagorean's theorem relates them. Okay. So you have to kind of know that kind of stuff. You have to know that stuff. So it says you're planning to make an open rectangular box from an 8 by 15 inch piece of cardboard. So let's draw a picture. So here's an 8 by 15 inch piece of cardboard. We're trying to make a rectangular box by cutting congruent squares from the corners. So these have to be squares. So these are all of these squares are going to be the same, and they're going to be X. This dimension has to be X by X. You understand? That's how you make a box. Otherwise it wouldn't be a box. And folding up the sides. What are the dimensions of the box of largest volume? So volume is what we're trying to maximize that you can make in this way. And what is its volume? All right. So the volume of a box is going to equal the length times width times height, right?
Yeah.
Well, what's the length going to be? In fact, I'm going to write this immediately in terms of X. The volume in terms of X, because I think we can see this. Do you see how this side right here is going to be, this distance right here is going to be the width. This distance is going to be the width. And that's going to be 8 minus 2 X's. Do you understand?
Yeah.
And do you see how this is going to be the length? And what's that length going to be?
15 minus 2x.
15 minus 2 X's. Good. And then what's the height going to be, of course?
I'm not sure.
Look at it and think about it. So it's 15 minus 2x times, so that's one of the dimensions. Here's another one of your dimensions. And what's the height? Think about folding that box up. What's the height going to be?
Would it be x?
Yeah, it's just going to be X. Good. So when I simplify this, when I distribute this out, let's do it like this: 15x minus 2x squared times 8 minus 2x. And now let's distribute. What's 8 times 15? Let's see, that's 80 plus 40 is 120. Check me, please. That's
Yeah, it's
120x. minus 16x squared, and then distributing the -2 in is going to give you a negative 2x, negative 30x squared, positive 4x cubed. So simplifying that, it's going to be 4x cubed minus 46x squared plus 120x. So there's my volume in terms of just x. And what am I trying to do? Trying to maximize that volume, right? So let's take the derivative of that. So power rule, 12x squared minus 92x plus 120. I do that right?
Yeah.
And now let's set this equal to 0. Now, you can, to set this equal to 0, there's a couple ways to do it. I'll be honest with you. You don't have to waste your time factoring if your teacher's okay. There was enough math in this problem. They don't want to see you factor necessarily. Maybe they do. But I would, if I were you, I would just take this equation, punch it in your calculator, and use your calculator to find it. Do you know how to do that?
Oh, we can't use calculator for tests actually.
Dang it. All
Yeah.
right. Well, that stinks. So let's see. What can we take out of these things? What can we take out? A 4 goes into it. I don't think a 12. Yeah, a 4. You can take a 4 out of this. You can factor a 4 out. This would be 3x squared. How many times does 4 go into 90? 4 goes into 80 20 times, and 12 more, so 23 minus 23x plus, check my math on this, please, plus 30.
Yeah, 30.
Okay, so let's see if we can factor this. Let's hope it factors. It probably is going to factor 3x and x and 30. Let's see, how about 10? How about minus 10? And no, 10 and 3 wouldn't work. Let's see, 5 and 6. Oh yeah, they're both gonna have to be negative. What am I saying? Yeah, it's gonna have to be 5 and 6. So negative and negative, so it's gonna be 6 and 5 somehow. How about 6 here and 5 here? Does that work? That's 5, that's 18. What's negative 18 and negative 5? Negative 23, perfect. So what are my answers? Let's set each one of those equal to 0. 3x minus 5 equals 0, and x minus 6 equals 0. So either x equals 6 or x equals 5/3. Now, can x equal 6? Look at my problem and tell me why I know 6 is an extraneous solution. Can you see why?
Oh yeah, because you can't do 8 minus 12 if you substitute
right.
in.
Yeah, it would be too big. So the only answer is 5/3. So what are the dimensions of the box of largest volume and what is its volume? So just plug in 5/3 into all of these different pieces here, plug 5/3 in here and here and here, multiply it out to get the volume, or just plug it into here and multiply it out, right? And that way it'll give you your dimensions. There's your width, there's your length, there's your height, and then your volume is just when you multiply them all together. I'm not going to waste the time to do that. You can do that on your own. Let's just set up these other problems because we only have like 5 minutes left. It says you are designing a rectangular poster to contain 50 inches squared of printing with 4 inches margin at the top and bottom and a 2-inch margin on the side. Okay, so we are a rectangular poster. Okay, here's my poster. There's a rectangular poster, and it wants to be 50 inches squared of printing.
Wait, actually, sorry, can we do number 36? Then it's
Sure.
a different type of problem than we done.
Yeah, no problem. All right, yep. Thanks for asking. How close does the curve come to the point? And the hint is if you minimize the square of the distance, you can avoid square roots. Okay, how close does the curve come to the point So this curve is going to come, the closest it's going to come to the point, you're trying to figure out what this distance is right here. So this is going to be a right angle. That's the closest it will come, is when that is a right angle. But it's not really a straight line, so it's hard to say that. It's hard to do that. Okay. Closest does the curve come to the point? So the distance here, whatever this distance is, we're trying to minimize the distance, right? So let's just find the distance. The distance formula is equal to the square root of x1 minus x2 squared plus y1 minus y2 squared. Is that right?
Yeah.
Does that look familiar to you? So this equals the square root of the x coordinate is going to be x, because that's my x coordinate, x minus 3/2 squared plus the y coordinate is square root of x, because that's what this equation is, square root of x minus 0, which is just nothing squared, right? So this is equal to the square root of x minus 3/2 squared plus x, because that x just went away. So that's my distance formula in terms of x, and we're trying to minimize that distance. So the hint says if you minimize the square of the distance, you can avoid square roots. Oh. Okay, so what they're saying is the minimum of this is going to be the same as the minimum of just what's inside here. You don't have to mess with the square roots. That's what this hint said. If you minimize the square of the distance, you can avoid square roots. You can avoid the square root here.
Oh, okay.
So to minimize to minimize this is the same thing as minimizing. We'll call it the square of the square of the distance. So we're minimizing s basically. So s is going to be the square of the distance. It's x minus 3/2 squared plus x. So we're trying to find the minimum of that. So we were trying to find the derivative of that. Okay, does that make sense? So if we distribute this out, it's going to be x squared minus 3x plus 9/4 plus x. Did I do that right? Negative 3/2 x plus another negative 3/2 x rather is negative 6/2, which is negative 3. Yeah, that's right. So this just becomes negative 2x. So the derivative of this is going to be 2x minus 2. So 2x minus 1. So where does it equal 0? At x equals 1. At x equals 1 is the answer. So how close does the curve come to the point? So so now I'm going to plug this number, because the question is how close does the curve come? So I need to find the distance. So take the 1 and plug it back into here for x. So what's d of 1? Are you following what I'm doing, or am I going too fast?
No, I'm following.
Okay, so the d of 1 is going to be 1 minus 3/2 squared plus 1, which is the square root of 1/2 squared, which is 1/4 plus 1, which is the square root of 5/4, which is the square root of 5/2. You want to check the answer key, see if that's right?
Yeah. Yeah, that's right.
All right, make sense?
So how did you know to use the distance formula?
Well, because that's they said, what is the distance? Remember, that's kind of the key with all these questions, is you have to kind of use your prior knowledge to figure out how I can, like what tools you need. So they said, how close does the curve come? Well, close means distance. So what's the shortest distance? The shortest distance is going to be, well, the distance, I should say, doesn't have to be the shortest. The distance is like, if this point right here, whatever this point to that point, the distance formula would be whatever that x is and whatever that y is, taking those coordinates and using it with these coordinates to find that distance. That's what distance formula does.
Oh, okay.
The distance formula just finds the distance. So when it said, how close does it come? I knew that I had to minimize the distance. I liked the little hint here because it saved me a lot of time. If I was trying to take the derivative of this thing, the square root of this thing, it would have been a lot more of a headache to do. I still would have gotten the same answer, but it would have been a headache to do. Make sense?
Yeah. So when they say to minimize or maximize, do they mean to take the derivative of the equation?
Yes, that's essentially what they mean. Because finding the minimum points and the maximum points in calculus has to do with taking the derivative and setting it equal to 0.
Oh, okay.